Groundwater. Groundwater is a critical component of the Earth's hydrological cycle and plays a vital role in sustaining ecosystems, supporting human activities, and maintaining overall environmental balance. It refers to the water that infiltrates and collects beneath the Earth's surface in saturated zones within soil and rock formations. This vast subsurface reservoir of water is a key source for drinking water, agriculture, and industrial processes. The replenishment of groundwater primarily occurs through the process of infiltration, where precipitation, such as rain or snowmelt, percolates through the soil and rock layers to reach the water table. This water is then stored in porous spaces, fractures, and other geological formations, creating underground aquifers. These aquifers can extend over large areas and vary in depth, serving as natural storage reservoirs for freshwater. Groundwater is a slow-moving component of the hydrological cycle, with flow rates often measured in meters per year. This characteristic makes it particularly susceptible to overextraction, as human activities can deplete groundwater resources at a faster rate than natural recharge processes can replenish them. Excessive pumping can lead to the lowering of the water table, land subsidence, and the intrusion of saline water into freshwater aquifers, compromising their quality and sustainability. Many regions around the world heavily depend on groundwater for domestic, agricultural, and industrial needs. In agriculture, for instance, groundwater irrigation is a crucial practice, especially in areas where surface water is scarce or unreliable. However, the unsustainable use of groundwater has led to concerns about depletion and the long-term availability of this vital resource. Additionally, groundwater interacts with surface water in complex ways. Springs, rivers, and lakes are often fed by groundwater discharging into them, influencing their flow and ecological health. Conversely, the overextraction of groundwater can reduce the flow of surface water bodies, affecting ecosystems and biodiversity. Monitoring and managing groundwater resources are essential for sustainable water use. Hydrogeologists and environmental scientists use various tools, such as groundwater modeling, to assess aquifer characteristics, predict flow patterns, and make informed decisions about water resource management. Implementing sustainable practices, such as recharging aquifers through managed aquifer recharge (MAR) projects, can help mitigate the impacts of overextraction. As the global population continues to grow and climate change alters precipitation patterns, the importance of understanding, protecting, and managing groundwater becomes even more critical. Sustainable water management practices, conservation efforts, and technological advancements in water treatment and purification are essential components of ensuring the availability and quality of groundwater for current and future generations. Groundwater flow. Groundwater flow is a fundamental aspect of hydrogeology, playing a crucial role in the movement and distribution of water beneath the Earth's surface. This subsurface flow is driven by the force of gravity and the pressure differences within porous and permeable geological formations, shaping the dynamics of groundwater movement in intricate ways. The movement of groundwater occurs within the interconnected spaces of soil, rock, and sediment, forming what is known as an aquifer. Aquifers vary in terms of their porosity and permeability, influencing how water flows through them. Porosity refers to the amount of open space within a geological formation, while permeability describes the ease with which water can move through these spaces. Well-defined aquifers may be composed of sand, gravel, or other porous materials that allow water to percolate and accumulate. Groundwater flow typically follows the contours of the water table, which represents the upper surface of the saturated zone. The water table can fluctuate due to variations in precipitation, groundwater extraction, and other factors. When the water table intersects the land surface, it gives rise to features such as springs, seeps, and wetlands. Groundwater can discharge into surface water bodies, such as rivers and lakes, creating a dynamic interaction between subsurface and surface water systems. The movement of groundwater is influenced by hydraulic gradients, which are variations in hydraulic head or water pressure within an aquifer. Water naturally flows from areas of higher hydraulic head to those of lower hydraulic head. This movement can occur horizontally or vertically, depending on the geological characteristics of the aquifer. Groundwater flow paths are complex and can be affected by geological structures, such as faults and fractures, which may act as preferential pathways or barriers to flow. Understanding groundwater flow is essential for various purposes, including water resource management, environmental protection, and the assessment of potential contaminant transport. Hydrogeologists use mathematical models and field studies to characterize aquifer properties, predict flow patterns, and assess the vulnerability of groundwater to pollution. This information is critical for making informed decisions about well placement, land use planning, and remediation efforts in areas where groundwater quality is at risk. Human activities, such as groundwater extraction for drinking water or irrigation, can significantly impact groundwater flow patterns. Overpumping can lead to the lowering of the water table and changes in the direction of flow, potentially inducing negative consequences like land subsidence or the intrusion of saline water into freshwater aquifers. As societies grapple with increasing water demands and the effects of climate change, a comprehensive understanding of groundwater flow is vital for sustainable water resource management. Balancing the extraction of groundwater with natural recharge processes, implementing effective conservation measures, and employing innovative technologies contribute to the responsible use and protection of this invaluable subsurface water resource. Groundwater extraction. Groundwater extraction, also known as groundwater pumping or groundwater withdrawal, is the process of withdrawing water from underground aquifers for various human uses. This practice is a crucial component of water resource management, providing a significant source of freshwater for drinking, agriculture, industry, and other societal needs. However, unsustainable or excessive groundwater extraction can lead to a range of environmental, social, and economic challenges. One of the primary purposes of groundwater extraction is to meet the growing demand for drinking water. Many communities around the world rely on groundwater as a primary source of potable water, especially in regions where surface water may be limited or subject to contamination. Groundwater, when properly managed, can serve as a reliable and resilient source of high-quality water for domestic consumption. Agriculture is another major sector that heavily depends on groundwater extraction for irrigation purposes. In many parts of the world, particularly arid and semi-arid regions, groundwater plays a vital role in sustaining crop production. However, the overuse of groundwater in agriculture can lead to aquifer depletion, land subsidence, and the degradation of water quality. Industrial activities also contribute to the demand for groundwater extraction, where water is used for manufacturing processes, cooling systems, and various other purposes. While industrial water use is essential for economic development, it can strain local aquifers and contribute to the overall stress on water resources. Despite its importance, the unsustainable extraction of groundwater poses several challenges. Over-extraction can lead to a decline in the water table, which is the upper surface of the saturated zone. When the water table drops, it can impact the availability of water for wells, springs, and other water sources. This phenomenon is particularly evident in areas experiencing groundwater overdraft, where the rate of extraction exceeds the natural replenishment rate through precipitation and other recharge mechanisms. Land subsidence is another consequence of excessive groundwater extraction. As water is withdrawn from underground aquifers, the soil particles may compact, leading to the sinking of the land surface. This subsidence can cause damage to infrastructure, such as buildings, roads, and pipelines, posing significant risks to communities relying on stable ground conditions. Moreover, the environmental impacts of groundwater extraction extend to ecosystems that depend on groundwater discharge into rivers, lakes, and wetlands. Alterations in groundwater flow patterns can affect the habitat of plants and animals, potentially leading to ecosystem degradation and loss of biodiversity. To address these challenges, sustainable groundwater management practices are essential. This includes monitoring and regulating extraction rates, implementing recharge projects to replenish aquifers, promoting water conservation measures, and adopting technologies that enhance the efficiency of water use in various sectors. International and local regulatory frameworks are increasingly recognizing the importance of sustainable groundwater management. Integrated approaches that consider the interactions between surface water and groundwater, involve stakeholders, and incorporate scientific assessments are crucial for developing effective policies to ensure the long-term viability of this critical water resource. Balancing the needs of human societies with the preservation of ecosystems is key to achieving sustainable groundwater extraction practices globally. Groundwater quality. Groundwater quality refers to the chemical, physical, and biological characteristics of water stored beneath the Earth's surface in aquifers. It is a critical aspect of overall water resource management, as groundwater serves as a major source of drinking water for communities around the world. The quality of groundwater is influenced by natural processes, anthropogenic activities, and the geological characteristics of the aquifer through which it flows. Various factors contribute to the determination of groundwater quality, including the presence of dissolved minerals, contaminants, nutrients, and microbial organisms. The composition of groundwater can vary significantly from one location to another, depending on geological formations, land use, climate, and human activities in the surrounding area. One common measure of groundwater quality is its chemical composition. Groundwater can contain dissolved ions such as calcium, magnesium, sodium, chloride, sulfate, and bicarbonate. The concentrations of these ions impact the water's taste, hardness, and its suitability for various uses. For example, high levels of certain ions, like chloride or sulfate, may render the water unsuitable for drinking or irrigation due to taste concerns or potential harm to crops. Contaminants, both natural and human-induced, are a significant concern when assessing groundwater quality. Natural contaminants may include minerals like arsenic or fluoride, which can exceed safe drinking water standards in some regions. Human activities, such as industrial discharges, agricultural runoff, and improper disposal of waste, can introduce pollutants like heavy metals, pesticides, fertilizers, and organic compounds into groundwater, posing risks to both human health and the environment. Groundwater quality is closely linked to land use practices. Agricultural activities, for instance, can contribute to groundwater contamination through the leaching of pesticides and fertilizers into the groundwater system. Similarly, industrial activities may release hazardous chemicals that can infiltrate the soil and eventually reach the aquifer. Microbial contamination is another aspect of groundwater quality, especially concerning public health. Pathogenic bacteria, viruses, and other microorganisms can enter groundwater through various pathways, such as septic systems, livestock operations, or inadequate sanitation practices. Consuming water contaminated with these microorganisms can lead to waterborne diseases, making the monitoring and treatment of microbial quality crucial for ensuring safe drinking water. To assess and manage groundwater quality effectively, regular monitoring programs are essential. Hydrogeologists and environmental scientists conduct groundwater sampling and analysis to understand the composition of groundwater, identify potential contaminants, and assess the overall health of aquifer systems. This data is crucial for developing strategies to protect and remediate groundwater resources. Remediating contaminated groundwater is a complex process that may involve various techniques, including pumping and treating, in situ bioremediation, and the use of permeable reactive barriers. Prevention measures, such as implementing best management practices for agriculture and industry, enforcing regulations, and promoting public awareness about responsible water use, are equally important in maintaining and improving groundwater quality. Given the interconnected nature of surface water and groundwater systems, integrated water resource management is crucial for addressing water quality issues comprehensively. Strategies that consider both the quantity and quality of water resources, involve multiple stakeholders, and incorporate sustainable practices are essential for ensuring the long-term health and resilience of groundwater systems. This holistic approach is key to safeguarding the availability of clean and safe groundwater for current and future generations. Please do not forget to subscribe to my channel, turn on notifications, like and share my videos and comment under my videos.